Hello everyone and welcome back. The goal for today is to talk about something called a higher order derivative, which basically is just asking the question, what if I calculate the derivative of a function more than one time? What if I calculate the derivative of a function and then take the result and calculate the derivative again? Is there any significance to that? Are there any situations where doing something like that would be useful? So we're going to practice calculating second and higher order derivatives of functions. We're going to talk about something called concavity. We're going to talk about inflection points, and then we're going to practice finding them. Now in video 14a, we said that the velocity was the derivative of position, in particular the derivative with respect to time. And we also said that acceleration was the derivative of velocity, again the derivative with respect to time. So acceleration must be the derivative of position. And this is an example of a situation where we would have a second derivative. The second derivative of a function f of x is denoted by f with two primes. This is sometimes called f double prime. F double prime of x is just the derivative of the function f of x. As an example, acceleration would be the second derivative of position. If you were given the position function and you needed to find the acceleration, you would take the derivative of position once to get the velocity, and then you would take the derivative a second time to get the acceleration. Symbolically, I might write something of this nature. So let's practice finding the second derivative in a situation like f of x equals x to the third power plus 10x plus 1 over x. The first thing that I want to do is find the first derivative of f of x. And in order to do that, I'm going to slightly rewrite this expression so that instead of having 1 divided by x, I have x to the power negative 1. Although it is technically possible to find the derivative of 1 over x using the quotient rule, it just takes a lot of time, and in this case using power rule can be more efficient. So using power rule, x cubed becomes 3x squared, 10x becomes 10, the exponent minus 1 comes down, and then minus 1 gets decreased and becomes negative 2. Now, to find the second derivative, all that I need to do is find the derivative of f prime. So I'm finding the derivative of 3x squared plus 10 minus x to the negative 2. 3x squared, the 3 becomes a 6 after it's doubled, and the x squared becomes x to the first power. The derivative of 10 vanishes, and the derivative of negative x to the minus 2 becomes positive 2 minus times negative 2, x to the negative 3. This would be the second derivative of the function f of x given above. In this case, we've calculated the derivative twice, but in theory, there's absolutely nothing stopping you from calculating as many derivatives as you want. Now, usually, once you go beyond the second derivative, the third and fourth and fifth derivatives are not quite as useful, not quite as broadly applicable. But every once in a while, you will run across a higher order derivative which actually is used in some applications. For example, if you take the derivative of acceleration, you get a quantity which is sometimes called impulse. The derivative of acceleration would be the third derivative of position. The nth order derivative, f2n in parentheses, is just take the derivative of f of x n times in total. If we returned to the same function f of x equals x cubed plus 10x plus 1 over x, suppose that someone wanted us to find the third derivative. Symbolically, they would write this as f with the exponent of 3 in parentheses x, third derivative. Now recall that we've already found the second derivative. This is the second derivative, and if I wanted the third derivative, I would just need to take the derivative one additional time. So that 6x would become 6, and then applying power rule to the term in the back, 2 times minus 3 would be negative 6, and x would be raised to the power minus 4. Negative 3, once again, decreased by 1 unit. Now, one of the uses of higher order derivatives was to give us convenient language for things like acceleration. Acceleration is the second derivative of position. But one of the more striking benefits of second derivatives is that it allows you to investigate a graphical feature of a function which is called concavity. We say that a function is concave up if the function's second derivative is positive. A function is concave down if the function's second derivative is negative. For example, let's consider the 4 functions listed below, and let's decide whether or not these functions are concave up or concave down. And in the first example, we have x squared, the quintessential quadratic function, a parabola that opens up. For x squared, if I calculate the first derivative, f prime, then by power rule, I get 2 times x. If I then calculate the second derivative, f double prime, then I just get this constant, the constant 2. Now the number 2 is definitely a positive number, and so by the definition, this function would be concave up. Conversely, if we had negative x squared, a parabola which opens down, in this case, f prime would be negative 2x. And therefore the second derivative would be negative 2, the constant. Because that second derivative is a negative number, the function f of x would be described as being concave down. What about e to the x? The graph of e to the x looks a little bit like this. And if I take the derivative of e to the x, nothing changes. If I do it twice, still nothing changes. Now exponential functions, e to the x, always produce positive numbers, which means that by the definition, e to the x would be considered concave up as well. But what if I did 1 over e to the x? 1 over e to the x is equivalent to e to the minus x, and so it's a horizontally flipped version of e to the positive x. It's coming down, looks like this. If I then take the derivative of 1 over e to the x, at this point we're going to need to use quotient rule. We will very soon see an easier way to calculate f prime, but right now the only technique that we have is quotient rule. So we would say the bottom function times the derivative of the top function minus the derivative of the top function times the bottom function, all over the bottom function squared. So if I clean this up a little bit, I know that the derivative of 1 is equal to 0. So that first term in the numerator is going to vanish. I also know that the derivative of e to the x is just e to the x. So I get negative e to the x divided by e to the x squared, and if I cancel common factors, I get minus 1 over e to the x. Literally just the opposite of what I had before. Now if you want to, you can go through this process all over again to calculate the second derivative, but I think it might not be the best use of time. I think the faster way to calculate the second derivative is to note that we're taking the derivative of something that's just minus 1 times the function that we had at the very start of the problem. We're taking the derivative of minus 1 times 1 over e to the x. So by constant multiple rule, you can pull that minus 1 out. Minus 1 times the derivative of 1 over e to the x, and we can use the fact that we already know that the derivative of 1 over e to the x is minus 1 over e to the x. We just finished calculating that. So f double prime would be equal to minus 1 times negative 1 over e to the x. In other words, positive 1 over e to the x. Now 1 is a positive number, e to the x is a positive number, so this entire number is positive, and therefore in the final case, we would also say that f of x is concave up. Now the question is, concavity, concave up versus concave down. Is there any relationship between the concavity of a function and the way that it looks graphically? Is there anything that the first and the third and the fourth graphs have in common that the second graph does not share? In order to answer that question, let's go out to Desmos. Let's have a look at the graphs of these functions, and what I'm going to do is I'm also going to have a look at the tangent line to these functions at various points. So graphed here, for example, is x squared in cyan, and the tangent line to the equation is given here in orange. And let's imagine, so here the tangent line is being affixed to the curve at this point here, which is given in purple. But let's imagine that I begin to drag that point in the positive x direction. As I move the point of attachment toward the right side, notice that the tangent line is beginning to pull upward. In the beginning it was pointing straight down almost, but as that point of attachment moves further to the right side, the tangent line is beginning to pull up more and more and more. So here we have the function x squared, and graphically we see that the tangent line pulls up as the tangent line's position moves to the right side. Here we have the graph of our second function, which we found was concave up, e to the x. Now this function was also concave up, and notice that as we slide the point of attachment to the right, that once again the tangent line is beginning to pull up and the slope of that tangent line is beginning to increase. So our second concave up function had this same property. As we slid the point to the right, the slope of the tangent line got steeper. Here is our third concave up function, 1 over e to the x. In this case as well, as we move a point of attachment to the right side of the picture, in the beginning the tangent lines are pointing almost straight down, but as we move the point to the left, the tangent line begins to pull up. It never fully becomes positive, but as we move it to the right, the slope of the tangent line is increasing. That tangent line slope is becoming less negative. Now let's contrast that behavior with our one example of a function which was concave down. This time, if we take our tangent line and we slide the point of attachment, notice that this is the only situation where we see the tangent line pulling down and tipping down as that point of attachment slides to the right. In the beginning, the tangent line was pointed to the top right, but the further we moved in the positive x direction, the more that tangent line began to dip downward. This is true for our concave down function. To explain this, let's go back briefly to our original definition of concavity. Now notice that concave up was equivalent to saying that the second derivative was positive. Now the second derivative is the derivative of the first derivative. That's a bit of a tongue twister, so let's make a note. Note, f double prime is derivative of f single prime. And we have a relationship between the behavior of a function and the sign of that function's derivative. For example, if f double prime is positive, then that implies that f single prime is increasing. Now remember that f single prime was the slope of the tangent line to f with no primes. So that means that the slope of the tangent line to the original function, f of x, is increasing. That is the behavior of a function which is concave up. If you're trying to determine graphically whether a function is concave up or concave down, think about whether the tangent line's slope is going up or going down as you move from left to right along the picture. Graphically, a function which is concave down has the property that the tangent lines begin to tip downward as you move from left to right. Whereas a function which is concave up graphically has the property that the tangent lines pull up as you move to the right. Now to date, we have been dealing with situations where the function was either completely concave up or completely concave down. But more realistic is the situation where a function is concave up sometimes and concave down at other times. So let's consider the function f of x equals x cubed. And let's try and answer the question, where is this function concave up versus where is it concave down? So the easiest way, in my opinion, to approach a problem like this is to calculate the second derivative. and to try and figure out where the second derivative is positive or negative. If f of x is equal to x cubed, then f prime of x is 3x squared. So applying the power rule one more time, f double prime of x would have to be 6 times x. On what intervals is the function concave up? These would be intervals where the second derivative is positive. Now 6x is positive where x is positive, and therefore the interval would be from 0 to positive infinity. Conversely, where would the function be concave down? The function would be concave down where 6x was negative. In other words, where x itself is negative. And therefore this would be the interval negative infinity up to 0. Let's see if we can confirm these results graphically. Here I have the graph of x squared in cyan and its tangent line in orange. Currently the point of attachment is down here in the vicinity of negative x's. Now I'm going to begin to move this point of attachment to the right side, and as I move it to the right, we can see that the tangent line is beginning to tip downward. In the beginning the slope was quite high, but the further to the right I move this point, the more the slope of the tangent line is beginning to decrease, until it seems to flatten off perfectly when we reach the point where x is equal to 0. That's a reflection of the fact that the function was concave down on the interval of x's from minus infinity to 0. But once I pass x equals 0 and I begin to move the point of attachment, notice that afterward, this time we see the tangent line beginning to pull upward. Now as I move the point of attachment to the right, we see that tangent line begin to get steeper and steeper and steeper, pointing more and more upward. This is a reflection of the fact that the function x cubed is concave up everywhere to the right of x equals 0. Now directly in between concave up and concave down is a point that's interesting enough to have its own name. An inflection point is a location where the function's concavity changes, where the function changes from concave down to concave up, or vice versa. For example, for this function f of x equals x cubed, an inflection point, and the only inflection point, was attained at this location where x is equal to 0, because the function was concave down everywhere to the left of 0, but then it switched to concave up. Now, what is important, what is interesting about inflection points is that when you're dealing with a graph representing a real-world situation, inflection points usually tell you, roughly speaking, when a trend begins to change. So Google Trends is a great source of examples of this, and in this particular problem, we're looking at the example of the Google Trends of how many people have searched for the word cyberpunk. Now what we see is relatively low levels of interest in cyberpunk until a rather incredible spike in the number of searches somewhere around the middle of November. This is when you're seeing interest go way up. And then somewhere around the middle of December, the interest reaches its peak and begins to decline. So looking at this graph, I would place the inflection point somewhere around here. Somewhere around here, the huge boost in the interest in this term begins to lose momentum. The momentum carries the interest to the peak for a little while, but then that interest begins to decline. Now let's compare the results on this Google Trends graph with the release date of the video game Cyberpunk 2077. Cyberpunk 2077 comes out in December 10th of 2020, which correlates quite neatly with this huge spike in interest in the term cyberpunk. So imagine, for example, that you're a YouTuber who makes videos about video games. Imagine that it's maybe December 10th, somewhere right between the 6th and the 12th, as indicated on this graph. By the time you acquire the game, play the game, record your footage, make your script, record your script, edit your video, and upload it, several days have passed. By the time your video is actually posted, it could be somewhere over here, December 13th through 19th, or even, unfortunately, December 12th through 26th, depending on how quickly you can get your hands on the game, how quickly you can do the editing, and how quickly you can finish the game to complete your review. So you start at around this inflection point, but by the time the video is actually done, the trend has already passed and people are starting to lose interest. That's one of the reasons why so many YouTubers are so passionate about getting early release versions of a game for journalistic reviews. In order to catch the wave of hype, in order for the algorithm to favor you, you need to start your review creation process before the inflection point. Only if you start the process before the inflection point can you hope to be ready by the time interest hits its peak, when you're the most likely to be picked up by the algorithm and to get lots of views. Now, when it comes to calculating inflection points, let's consider the following exercise. Calculate the x values of the inflection points for the function f of x equals sine of x. To that end, what I'm going to do is I'm going to calculate first the first derivative, then the second derivative, to try and see where the second derivative might change from positive to negative. Now we know that the derivative of sine is equal to cosine. We also know that the derivative of cosine is equal to negative sine. To answer this question, my preference is to have a look maybe at the unit circle. Whenever sines and cosines are involved, the unit circle is not a bad idea. Now, sine of x changes from positive to negative at these two locations marked by x's. We begin with some angle, and as that angle increases, when that angle points to a location above the x-axis, sine outputs a positive number. Then the angle is pointing to a location which is below the x-axis, which causes sine to change from positive to negative. And as you continue to spin around and around, sine of x changes from positive to negative, or from negative to positive, every time the angle passes through the positive x-axis or the negative x-axis. Now, if sine is changing between plus or minus, negative sine is definitely also changing between plus or minus. So the inflection points are located at multiples of pi. Zero, 2 pi, 4 pi, corresponding to the right half of the unit circle, pi, 3 pi, 5 pi, etc., corresponding to the left half of the unit circle. So I could write, for example, k times pi, where k is an integer. K is an element of the set called z, the set of integers. Now, just as a word of warning, when you're looking for inflection points, you cannot find inflection points by solving f double prime of x equals 0. It may seem tempting as a result of the intermediate value theorem to say, well, f double prime is changing between positive and negative, and anywhere that occurs at a location where f double prime is 0. And that is true. Any inflection point must be a solution to this equation. But the problem is that there are some solutions to this equation which are not inflection points. So let me represent that by a Venn diagram. Big circle, everything inside the big circle is a solution to f double prime of x equals 0. Inside that collection are all the inflection points. But if you're trying to answer a question like this one, just by solving f double prime of x equals 0, there is a chance that you are going to get some x values which are not actually inflection points. Let me give you an example. Let me give you the function f of x equals x to the 4th power. If I calculate f prime, I get 4x cubed. If I calculate f double prime, I get 12x squared. Now take a moment and acknowledge the fact that 12x squared is never negative. Because 12x squared is never negative, it's not possible for the concavity to ever become concave down. Nevertheless, there is a solution to second derivative equals 0. This is achieved when x is equal to 0. So this would be an example of a point which makes f double prime equal to 0, but which is not an inflection point. This function does not have any inflection points because it is never concave down. X equals 0 would be an example of one of the points which is a solution to f double prime equals 0, but which is not an inflection point. So you really do have to go through this process of asking yourself the question, where does the sign of f double prime actually change? Where does f double prime actually switch from being positive to being negative, or vice versa? No shortcuts here. Okay, that concludes today's material. We talked about second derivatives and higher order derivatives, how to calculate those. Then we talked about concavity, what it meant graphically, and the consequences that it had in terms of the sign of f double prime. We talked about inflection points, what they represent in real-world scenarios, and some ways that they could be calculated. You're looking for locations where f double prime changes sign from positive to negative or vice versa.